Hello everyone. Today we are presenting our project synthesizing stereo 360-degree images. This is a team project proposed by An and Shiqing from the Department of Information Sciences and Technology at George Mason University. Our project is about enhancing user experience of 360-degree images. So here we will talk about the definition of 360-degree images. A 360-degree image is a panoramic image that surrounds the original point from which the shot was taken. Users can usually view this kind of images inside a head-mounted display, and they are allowed to switch their viewing directions of the panoramic contents by moving the HMD around. Currently, the 360-degree videos are supported in major video websites such as YouTube, Meta, or Vimeo, so we can see they are becoming more and more popular. And also, this technology is a great advancement in providing immersive multimedia experience to users. Although the 360-degree image is an advancement towards immersive multimedia experience, it is still not the real immersive multimedia experience. So here we will talk about what truly defines the immersive multimedia experience. Specifically, real immersive multimedia experience allows users to perceive the depth information of all the 3D objects in the virtual environment. And to achieve this goal, users are provided with stereo images. And specifically, stereo images are those images which contains two slightly offset images, separately shown to each eye of the user, as shown in the figure below. We can see the two cubes inside the images are not quite the same, and on the left side, the left subfigure is shown to the left eye of the user, and the right figure is shown to the right eye of the user, and in the perspective of the user's view, the users can see and feel the offset of this cube object, and the users can feel that this object actually comes in 3D rather than a 2D picture. And here is the situation of the current 360-degree images. So currently 360-degree images are recorded by only one camera. Therefore, it contains only one panoramic image, and this same image is rendered to both eyes of the users. Therefore, it is not a stereo image, and as a result, the users cannot perceive any depth information from the image. In another word, the users will feel like they are surrounded by a 2D panoramic picture, but they will not feel they are immersed in the 3D virtual scene. Here are some solutions for this limitation. One way is to stop the monocular 360-degree image recording and start stereo 360-degree image recording from now on. Specifically, instead of using one panoramic camera to record the image, we start using two panoramic cameras placed aside each other and start recording the image at the same time. So in this way, a pair of offset 360-degree images can be generated, and once this pair of images are displayed to each eye of the user, the depth information is perceived and the real 3D immersive multimedia experience is provided to the user. However, this method will double the equipment cost to record a 360-degree image, because it requires two cameras, And also, this solution does not truly solve the problem because all the existing 360-degree images are still monocular. So a great part of those experiences are still poor for the user. In order to enhance the user experience in the huge amount of the already published 360-degree images, another solution is proposed. This solution aims to convert the monocular images into stereo ones with the assistance of machine learning technologies. Ren and Lee's team designed a deep neural network to first predict depth information in one image, and then with some handmade algorithm, the other offset image can be generated with this predicted depth information. And when this pair of offset images are rendered to each eye of the user, the stereo images is finally generated and delivered to the user. However, the network proposed in the related work cannot be directly applied to our case, because their network was designed for regular images, while in our case we have 360-degree images. And in order to feed a 360-degree images to the neural network, we first need to convert the image into an equirectangular image, as shown in the figure below. And we can see in the figure, in this equirectangular form, all the objects inside the picture are distorted to some extent. Therefore, if they are directly fed to the neural network, the predicted depth information will not be accurate, and then the further synthesized stereo images will also not be accurate. Therefore, the user experience of this kind of enhanced stereo images won't be promising. Inspired by the previous work, in this study we propose to take a step further. We aim to design a deep neural network to create stereoscopic 360-degree images from monocular ones. So a monocular 360-degree image is directly enhanced into a stereo one. And this solution does not need two cameras for the image recording, so the equipment cost is minimized. And most importantly, using this technique, all existing monocular 360-degree images can be enhanced into stereo images. So all users can enjoy real immersive multimedia experience. Here we talk about the implementation status of our data collection process. First of all, we have some requirements of our data quality. As we all know, data quality is crucial for the model training. So specifically, we have the following two requirements for our data. First of all, the data must be some videos that are panoramic. In other words, it must be 360-degree videos. And the second requirement is that the video must be stereo. In other words, each frame in the video must contain two panoramic images, one rendered for the left eye and the other one rendered for the right eye, and the two images should be a little bit different from each other. And here we talk about the data source that we used. We use the YouTube platform as our data source because it is the most popular video sharing platform worldwide, and it has abundant 360-degree videos available for us. And most importantly, it has a result filtering function that allows us to conveniently pick the stereo and 360-degree videos to meet the data quality control that we need. Here is the implementation of the data acquisition step. We use the third-party library function named ytb-dl to download 360-degree stereo videos from YouTube. The reason why we use this third-party library function instead of manually download videos one by one on the YouTube website is that this third-party library function allows us to download a group of videos simultaneously, which is more time efficient. So specifically, we first manually selected 25 stereo 360-degree videos and stores their name and web address in a list. And then we implemented a script to automatically read the name and the website address in this list and download all of them simultaneously. And here is the implementation for the data preprocessing step. So basically, we implemented a script to randomly extract 40 frames from each of the video. And interesting thing worth noting here is that we can see that the 360-degree stereo videos have a different encoding format as shown in the two figures below. So one type of encoding format is as shown on the left side. We can see when we download the stereo video, we can see in each frame it actually contains a upper half and a lower half. So the upper half image is the image rendered for the left eye, and the lower half part is the image rendered for the right eye. And the other type of formatting is as shown on the right side in this figure. We can see that this figure is actually cut it up into 4 pieces. So the entire left part contains 2 images. So both images are actually rendered for the left eye. And the 2 images on this right half is both of them are rendered for the right eye. So basically, this script we wrote, it actually needs to check which format this video is using, and if it's using the format on the left side, then it will cut each frame in half horizontally, and the upper half will be used as the data for the left image, and the lower half will be used as data for the right side image. And if it's using the format as shown on the right side, then it will cut this image, it will cut each frame vertically, and the left half part will be used as the data for the left image, and the right half part will be used as the data for the right side.
Let's discuss the overall design of the stereo GAN. The burst view of the stereo GAN including 3 main components: the generator, the discriminator, and the loss function. We will go into the detail of these 3 components in the next slides. The overall working flows of the model is following. First, we have an image on the left side. It's input to the generator. The generator will produce a synthetic ray image. The discriminator will receive either synthetic ray image or the genuine ray image one at a time, and it will output 0 or 1, meaning either the image is fake or genuine. And then the loss function will measure the performance of the discriminator, and this loss function will allow the generator and the discriminator to update its network parameters during the learning process. Now we will discuss each component in detail. Next, we go into the detail of the generator. As you can see on the figure at the bottom of the slide, the generator consists of multiple convolutional layers stacked on top of each other. Here we're following the encoding-decoding architecture where the first few convolutional layers will try to reduce the size of the feature map. This basically compresses the information from the image. And then the middle part, about 8 convolutional layers, will try to encode and represent the image feature. And the last few layers will expand the feature map. The last layer will produce the final synthetic right image. Now, let's go into further detail of this figure. As you can see, there are several numbers on each layer. The first number is the number of feature maps. The second one is the kernel size, and the third one is the stride. Stride equal to 2, meaning that it will reduce the size of the feature map by 2. On the other hand, the counterpart of the stride is equal to 2 is the scale up layer, which is color red here. Every time this layer is applied, the size of the feature map will double. And we use 8 convolutional layers total in the middle part for feature representation. Next, let's discuss in the detail of our discriminator. The figure on the top of the slide shows the structure of the discriminator. This model will receive an image supposedly on the right of the stereoscopic pair, and this image can be either genuine or fake, and the model will output a number ranging from 0 to 1. 0 means the model decides this image is fake, and 1 means the model considers the image is true. And the structure of the model is as following. We inherit most of the model structure of the generator and bring it into the discriminator. As you can see, the discriminator also have the encoder and 8 layer used for feature representation. What different is that it have another 2 convolutional layer with the stride equal to 2, and the final layer is have 1000 filter map. Then we will have a final decision layer, is a fully connected layer that will receive a vector of 1000 elements, which is the output of the last convolutional layer, and output one number ranging from 0 to 1. By doing this, the model will be able to make a decision on the true or fake of an input image. The final piece in our design is a loss function. The loss function must reflect the difference between the input of the output of the discriminator. In our case, the discriminator output a number p, which is a continuous value from 0 to 1, and the ground truth is a value, an integer value taken from the set of 0 or 1. So in order to reflect this difference, we use a cross entropy loss, which the formula described below. The general idea is that the entropy of y and p will return a very large positive number if y and p are different. For example, y equal to 0 and p is equal to 1, means they have a very large difference. Let's discuss about our implementation approach. The graph below showing the 3 components of our project: the dataset loader, the GAN module, and the evaluator module. Let's discuss each module. The dataset loader its main job is to read images and label from the disk and transfer it to the GPU. It also organizes the data in the dataset by splitting the data into the training and the test set. The tool for us to implement the dataset loader is Python and PyTorch. The second module is the GAN. Here we perform model prototypes and model implementation, and then we perform training and evaluation. Our main tools for this module is PyTorch and CUDA. CUDA is a framework allows us to interact with the GPU, and the PyTorch is a very popular deep learning library. The last module is the evaluator. Its main job is to extract the result from the GAN module, doing some number crunching and visualize the result. To carry out this task, our main tools for this module will be Python and Jupyter Notebook. Jupyter Notebook is a very popular tool to visualize the result and graphing plots. Overall, the whole pipeline uses the Python language. Next, let's discuss about the benchmark that we use for our project. So the baseline here we decide to use is a non-generative convolutional neural network. Basically, we want to emphasize the advantage of using a generative model and how it will impact the image quality. In order to do this, the basic TCNN, it will inherit the basic structure of the generator. So it is only different in the way that our model and the benchmark, the baseline learn, is that the baseline, it will compare directly the synthetic image with the ground truth image, and it will measure the pixel-wide distance and try to learn the network to produce an image that identical to the ground truth. On the other hand, the image generated from our network will be put into the discriminator that will force the generator to learn the underlying distribution of the data, not just the pixel itself.
Here is the current status of our dataset collection process. So as talked before, we extracted 40 random frames from each of the videos, and in total we have 25 videos. So as a result, we extracted 1000 frames from all the videos, and since the videos are stereo videos, so each frame actually contains two images, one image for the left eye and one image for the right eye. So in total we have generated 2000 images. Half of them are for the left eye rendering and half of them are for the right eye rendering.
Here is our current implementation status of our project Stereo GAN. We have already finished collecting a certain number of videos from YouTube, and we already write code to integrate the dataset, meaning we write code to create a label, write code to create a train and test set, and the label is ready to be dumped into the GPU for model training. And as shown in the previous slide, we already finished the model designing of the loss function, the generator, and the discriminator. We are currently in progress of the model implementation in PyTorch. Once we finish this implementation, we will finish our next task, which is show as to be done. So our next task will include, first is to expand the training set. We need to expand the training set large enough so that the model won't be overfit so much. We don't know exactly what is the number of data we need right now, so this is to be discussed. Then after the model is trained, is ready for is already been implemented, we will proceed with model training. And verification. Verification here means we will quick check the model performance and make some small adjustment if needed. Then we will repair the baseline. Now the baseline will take a significant time because we need to train a model again and on a new loss function. But thankfully, we already have the code during the model implementation step, so this would reduce a lot of time. And finally, we will try to get the result, compare the model with the baseline, and getting some graph for this. So here is our conclusion. In this presentation, we discussed the design, the implementation approach, and the benchmark that we will use for our stereo GAN. And in the next step, we are going to focus on the model training. And after the training, we will compare the result with the baselines and prepare for the report. So that's it for our presentation. Thank you.